Thank you for inviting me to give a talk. I wasn't sure what the topic was going to be, but I wanted to give a talk that would hopefully sort of inspire the community and give people a chance to think about ambitious science goals that face us in the future. So the title is How to Model a Living Planet. And so hopefully that title makes more sense in the coming minutes. I should say that it's midnight here in Tokyo, so forgive me if I'm not my sharpest. Um, so let's move right into it. I want to talk about three big challenges I think that we face in the field of geodynamics. One is multi-scale planetary physics, how to connect the atomic scale to the planet scale and everything in between, and how those things interact with each other. The next one is planet behaviorism, which is complexity in planet evolution and memory effects, hysteresis, stochasticity, etc. The third topic is what we're calling planetary metabolism, the science of living worlds. The idea is to develop a whole planet deep time open systems process science, which has implications for habitability, sustainability, and other topics. Oops, is it going to go? There we go. So let's go to multi-scale planetary physics. I just have a slide in here about some issues in multi-scale physics for the dynamics of fluid parts of the planets and moons, particularly with dynamo, with respect to the dynamo. I think turbulence is a really big issue, which connects, of course, the large scales as kinetic energy is propagated to small scales where it's dissipated. We really don't have a suitable theory for MHD turbulence that's applicable to the dynamo or for situations involving stably stratified regions and other complicated scenarios. We also have a problem with rapid rotation. Resolving the Ekman layer will never be plausible, probably computationally, so we need some robust methods to upscale it. And then there's time scale issues, modeling the dynamo and understanding how it behaves over scales relevant to geological observations is always going to be a challenge. But there's going to be another talk after me. I think Julien Aubert and his colleague will discuss more on these things. So I want to get to scales that are relevant to dynamics of rocky parts of planets and moons, going from the atomic scale to the global scale. So at the atomic scale, we have vacancies and diffusion and things like this, which are very fundamental phenomena that happen at the very smallest scale, but they feed back into the largest scales and they determine what's going on at the largest scales. But in between these largest and small scales, we have a lot of other phenomena and phenomenology, which we usually gloss over, I think, in our models, and we haven't really dealt with. We have the subgrain scale, there's dislocations, dislocation dynamics. There's a lot of cool work going on in that field right now that's changing our view of how mantle minerals deform. There's grain scale dynamics, rock scale, zone scale for like shear zones, plate boundaries, crust thickness scales, and ULVZ scales, phase changes. These things are really important. There's mesoscales, regional scales, etc. All of these scales have different things going on and different physics that's relevant to them. And these are very complicated processes. They all have hystereses and nonlinear feedbacks. And the thing is that we don't really understand how these scales interact with one another to produce the collective dynamics of the solid regions of the planet. I think this is a really critical thing for us to address. We often assume, and as we have for almost the past century, that the mantle behaves like a fluid, we say, which was a useful abstraction, maybe in the 1930s when people were developing theories. Computational fluid dynamics wasn't, of course, available yet, but the mathematical theories were developing, laboratory experiments on convection, and a lot of really neat concepts were developed that started to make sense about what the mantle was doing beneath the lithosphere. Even theories about how continents can come together and pull apart. If you go to a more modern book, Schubert, Turcotte, and Olson, probably almost everybody here is familiar with that, and you go through their chapter on mantle rheology and mantle viscosity, it basically ends with this kind of description. You have diffusion creep and dislocation creep. the thing is that there's vastly more mechanisms that are able to accommodate deformation in the mantle than these two things. But they just kind of leave it there, and we're supposed to sort of believe. And I don't want to give these guys a hard time. I love, Jerry, Don, and Peter. They're great guys, and they've done a lot of really amazing work. But it's left to be the imagination. How does this processes that are happening at the atomic scale just map straightforwardly to all of these other scales with no interactions, nothing happening in between them? There's nothing going on. It really stretches credibility, I think, for anybody, especially who looks at a lot of rocks. When somebody says behaves like a fluid, what do I mean by a fluid? I think we all have basic fluid conceptions. We're around water, we drink water, we bathe in water, hopefully. Um, what does a fluid do? It deforms, of course, under deviatoric stress. The mantle does so. The surface of the Earth conforms to a balance between rotation and gravity. So we know that it holds a shape that seems to indicate that the interior is deforming and kind of in some sort of dynamic equilibrium. We know that probably where there's stress, there's increased strain rates. These are things that fluids in the mantle seems to do the same. Fluids have a diffuse deformation pattern. If you shear them, they seem to have a very distributed deformation pattern. Whereas the mantle, at least what we can see of it, if we look at plate tectonics as a proxy for what's happening inside the mantle, we don't often do so, but we could. Then we see things like shear localization. We see strong hysteresis and memory effects, whereas fluids have no memory. And it's really important because the areas of disagreement between what we would consider a fluid and the rocky mantle are the really fundamental drivers behind phenomena like plate tectonics or preservation and mixing of isotopic heterogeneities in the mantle, things like this, which are really the frontier topics in deeper science. So we spend a lot of time, we start with a fluid assumption, and then we try to reverse engineer it to back out something that looks more like the Earth. Of course, Tackley and others have for many years used the yield stress rheology, which is a fluid rheology. It gives plate-like behavior, but there's no memory effect. And I think the rheology is unrealistic. It's the kind of parameters that you have to use and put into the model to make it work are not anything like we would expect in the Earth. There's more recent work on grain size reduction, which can accelerate diffusion creep, and perhaps hysteresis and memory via Zener pinning and other mechanisms. There's also new work on weak phase interconnection, the strain weakening observed in lab experiments in a mixture of bridgemonite and periclase by Corrado and others. And this seems to indicate that strain weakening is a phenomenon that could occur in the lower mantle, not just in the lithosphere. So this opens up many interesting possibilities. We have a lot of work ahead. This is just a small sample. This isn't a review talk. I don't have time to go into a lot of this, but we're heading in this direction, but we still have a long ways to go to connect all these scales. So I'm going to get into planet behaviorism next. And I just want to throw out a question as an example of planet behaviorism. Is planet evolution deterministic or is it stochastic? In other words, if you start off a planet's evolution with a certain number of inputs, composition, temperature, mass, etc., and you get some outcomes, which are a function of those inputs, you always get the same outcome if you put the same inputs into or an input plus epsilon. Does it give you something close to what input without epsilon gives you? Or does it give an input, yield different results? And the best you can do is map it into a probability distribution. This is shown in this slide. So in the deterministic in pink here, you have input A gives you outcome A always, input B, outcome B always. But in a stochastic model, input A could give you A, B, C, D, or E, and the probability of each one can be different. It need not be normally distributed either. You could have input B where there's very divergent scenarios and they could be almost equally probable. But something small can happen. So how does a stochastic dynamics work? Why would you have this kind of behavior? I'll just use a brief example from something that's unfortunate, the pandemic that's ongoing, but a lot of people have been studying epidemiological models. Maybe some of you are aware of this SEIR model for susceptible, exposed, infected, and recovered. It's just simple differential equations which describe um, the evolution of an epidemic. And it gives you very simple solution behaviors. Everybody's probably familiar with this kind of peaks in infected. You see this in the lower right plot here. This is the kind of classical scenario for epidemiological models. It's a deterministic model, same inputs give you the same outcomes, etc. Now, when you look at the data, now this isn't supposed, you're not supposed to be able to see any particular country's pattern here. You can go to this website and explore. It's kind of interesting to look at. Maybe some of you already have done so. But it's very difficult to find any country that has a simple behavior like any sort of deterministic model can give. The other thing is that there's been a widely variable outcomes in the pandemic. And sometimes a country will do very well and people are like, why? They did everything wrong, it seems, but they're doing well. Or a country does, has very poor outcomes and they seem to do everything right. And then there's the opposite, the flip sides of all those. But there's been a lot of discussion about this among the epidemiological community, and they've turned to the idea of stochasticity. One of the things that keeps coming up is this idea of super spreaders, which has been shown in laboratory experiments. A person who's infected can emit very few viral particles or a modest amount, and then there's just a few people who emit an enormous amount, and we don't really understand why. But when you have this kind of heterogeneous agents that are working in the system, it changes the dynamics and you get very interesting behaviors. This is just some examples. It's certainly not comprehensive. In case one, you can imagine a normal spreader who's in blue comes in and they don't spread it to anybody else. So that's the case R equals 0. The epidemic is just one person and it's all over. Case 2 is where normal spreaders infect other people, usually just one other person, sometimes 2. And it spreads like a diffusion process and it happens relatively slowly. These are typically easier to contain, and this is how a lot of infections spread. Case 3 is you have a super spreader and they come in and they just infect a whole bunch of people. And if they just infect people who themselves become normal spreaders, then maybe it slows down and you can isolate the cluster and then suppress it and contain it. The case 4 is the worst case, and this is the cases where maybe things have gotten out of hand. So you have a super spreader which affects enough people that it creates other super spreaders and they beget other super spreaders and so on. And then it's like it reaches a sort of percolation threshold and the spread of the coronavirus just goes crazy through the community. And we've seen this kind of happen in several cases, and people are looking at this right now. Well, okay, let's bring this back to geophysics. And this idea of like a mantle super spreader. So you can have so this is the paper from Girard et al. From Corrado's lab in 2016. So basically what's going on here is I have a mixture of bridgemanite and periclase, which is what you have if you take pyrrolite in the lower mantle. Bridgemanite's a very strong phase, periclase is a very weak phase. If you subject it to stress as a uniform mixture, then the strain has to be distributed more or less. But if the periclase grains can connect to each other, then being much weaker than the bridgemanite grains, they can facilitate a lot more shear, and you get these little narrow shear zones developing in the fabric. This is what they claim to see, is basically a strain weakening effect. And this is how heterogeneous agents can sometimes work in systems when you have something, even if it's a relatively small component, it can have a very large effect. What about a stochastic planet? So where you have input B and you have this kind of divergent outcomes. Maybe one of those outcomes is a planet that has plate tectonics. Maybe another one is one that has rigid lid. Our models are not anything like this. We would have to think about how to approach this kind of question if we were to try and model it, how to even construct them. Also how to convey and account for uncertainties. And I think that the other thing is we can think about new opportunities for modeling strategies that we don't currently employ if we want to explore these kind of things. That's something to think about. Okay, planetary metabolism. So when I say process, what I mean by process is something that utilizes available energy to transform the state of matter from one state to another. That's all it is. So the process is the thing that connects the initial state and the final state. And geological processes are what shape the planet, and I think that also life is a geological process, but that's something that would take a longer talk to explain. I think geology is fundamentally about the study of process. You know, what happened in the past to transform matter into the rock record that remains today. If that weren't the case, then we just look at a rock and say, ah, it's a rock. You know, who cares? But we actually do care. Geodynamics is fundamentally, I think, about modeling geological processes and rendering quantitative predictions about their outcomes and interactions. We can think of a lot of geodynamic phenomena, including atmospheric dynamics, crustal dynamics, throw seismology in there too, plate tectonics, rotating convection, geodynamo, doubly diffusive convection. Through all these things, you could see them as being collaborations between simpler processes. These simpler processes get together and they produce these collective processes that we're interested in studying. And I think this process view can be very fruitful in a lot of ways. If we take this one step further, for example, we could think about, and this is the getting to the concept of planetary metabolism, is where you have these processes that are collaborations of smaller scale processes that are contributing to them, working together, and you have feedbacks, and these arrows basically represent a process interaction and the directionality of it. Two-way arrows means it goes both ways. And I put here autotrophic and heterotrophic life. And classic symbiosis, of course, is connecting these different components of life. If you have this concept of syngiosis, then it basically expands that concept to include all geological processes happening in the planet, from the geodynamo to weathering and erosion, and with inputs from stellar fusion and other things. So this is, I think, something to try and move towards in understanding how do we make a living planet? Is a planet habitable? And is a planet, are what we're doing, the way we're living on this planet, sustainable? You know, we should start to think about these systems and build up these understandings. I'm just gonna, that's kind of redundant. There's more follow-on topics I could discuss, but again, I don't have a lot of time. You know, diversity, ecology, and evolution of planets at stellar and galactic scales, planetary biographies, and so on. This is, I guess, being recorded for posterity, so you can come back and look at it later if you're interested. I want to use the remaining couple of minutes just to get on a soapbox for a second and talk about CIG. I've been familiar with CIG from its very early days and its conceptions, and so I think I'd like to make a few points. You know, I think everybody should always ask, as a community or whatever enterprise they're involved in, you know, what are we doing? Where are we going? What is our purpose? And how are we relevant? You know, what are we aiming at? And these are good things for us to think about as a community, and CIG is maybe an opportunity for us to get together and have these kind of discussions. I think that at the present time, geodynamics in the deep earth is not a predictive science. You know, our models rely on numerous assumptions, and there's a lot of uncertainties. And as I mentioned before, we're missing some fundamental pillars of our science, especially the multi-scale model, the standard model of geodynamics in analogy with the standard model of particle physics. You know, we need to have a critical self-assessment and think of things and look at and be hard on ourselves sometimes, or say, you know, humans, we have a tendency to fall into ruts. We do that. We all do it. It's easy to just turn the same crank, recycle the same concepts, and write the same papers that nobody reads, and sit in comfy office jobs, obtain, you know, et cetera, et cetera. But that enterprise, if we get too stuck in the rut, it's going to grind to a halt. It's not going to work out. We're going to lose relevance, respect, jobs, funding, et cetera. The other problem is I don't think any one of us wants to do that. I mean, we all got into this because we wanted to do some really cool science. And so I think these are something for us to think about. if we are stuck in a rut, if that's what we find, can we use CIG as a vehicle to help get us out? I'm not saying that CIG has to lead the effort, but CIG can be a very useful, powerful force to maybe help bring the car out of the rut. And I just want to leave with this slide. CIG's for what's the role and what's envisioned in the community. Is it going to be a boilerplate tool developer? And I don't mean that in any disparaging way. It's incredible what CIG has accomplished to date. I think it's come a long ways. I'm very impressed. The skills of the developers and the software that's come out in CIG in recent years is just amazing. I'm very impressed by that. But now that we've gotten there, is that something to continue doing, or is there something to do next or to think about next? One thing I think that we might ask is whether it can enable frontier science, like expand the field, move the frontiers out, and become a catalyst for science that can only be advanced at a community level with community level resources. And so I'm just going to end there. I'll leave the slide up. I'll be available for further dialogue in the discussion forum for this workshop if somebody wants to continue. I don't know how late I can stay up and be coherent. So with that, I'll end the talk. Thanks.